Hello and welcome to this episode of Physical Attraction. We have a guest on the show today, Professor Lewis Dartnell. Lewis is an author, presenter and Professor of Science Communication at the University of Westminster, and he has written and researched on topics as diverse as astrobiology, how to rebuild civilization after the apocalypse, and the influence of Earth's geology on the history of development of the human species. I first came across Lewis's work reading an excellent book he wrote, The Knowledge, which is essentially a how-to guide on how one might try and restart civilization after a cataclysmic event. We talked about the book and the prospects of finding life in the universe in this interview, which I really enjoyed. Without further ado then, the interview. Hi Lewis, so first of all, thanks very much for coming on the show.
Thank you for having me, Thomas.
So the main reason I wanted to talk to you is about your book, The Knowledge, How to Rebuild the World After an Apocalypse. But later on, if there's time, we can talk about astrobiology, which is your main field of study. The Knowledge, this fascinating book, it feels really relevant in the modern day. We're seeing a real stress test to our global civilization taking place with COVID-19 and its aftermath. And this book essentially tries to answer this question: if modern civilization vanished overnight and a small band of survivors had to start again from scratch, what would be the most important things that they would know, that they would need to know to get it kick-started again? So I'd like to ask sort of how you came up with this idea and how you went about researching and trying to answer this specific question.
Yes, that's the premise for this book. So for my last book, The Knowledge, which is a thought experiment. I feel like I should point out as quickly as I can that I do not think the world is actually about to end. I do not think civilization is on the brink of collapsing in the coming year or two. I'm not a prepper. I'm not a survivalist. I don't have the end of the world is nigh placard around my neck sort of thing. But as a scientist, I was curious to be able to answer this question about if it were to happen, if there were this hypothetical scenario that we're all familiar with from The Walking Dead or The Last of Us computer game or any number of other movies or TV series, if that were to actually happen, and the sort of technological civilization rug were pulled out from beneath our feet, how much would any of us actually know about how to make or do all the things that we just take for granted in our everyday lives? How is our modern existence being provided for invisibly behind the scenes by modern industrial civilization, and how much we've kind of lost that connection to that basic knowledge that our grandparents had this understanding of, but we've kind of lost. We've kind of atrophied those survival, crafting, maker skills. So I thought that the cleanest way to be able to ask that question, to then spend the book exploring it, was to imagine that you've woken up tomorrow and the world as we know it has just puffed out of existence. It doesn't matter if it's been some kind of asteroid strike or a super volcano eruption, or what is feeling quite prescient now in the book, some kind of global pandemic starts spreading rapidly around the globe. If that were to happen and collapse civilization, what would you most want to know? What would you most want written down in some kind of quick start guide to rebuilding civilization itself? Could you reboot the entire world? Could you reboot civilization the way you would reboot a computer after it crashed? And so that's what I sat down and set out to try to do with The Knowledge, with this last book.
So one of the things I found really interesting about the book is how it bends genres together in some ways. So some of this vital information is these survivalist tips and tricks, like how to make rudimentary medicines, which seeds to grow in which climates. Other aspects are things like basic scientific principles, like the germ theory of disease, which took us many, many centuries to come up with when you sort of look at humanity's development historically, but which would have saved us a lot of time and effort if we knew about them earlier. And there's also these practical engineering blueprints for building machines, things like lathes and looms and so on, which come in handy a bit later on as you've developed civilization a little bit more. So there's this real synthesis of genres. So when you were choosing which knowledge to include, do you think that your thought process about what to include changed over time as you were considering the practical reality of the situation? How did you pick which things were most important to include?
So clearly there is a massive sleight of hand in this book. That the premise, the conceit for the book, is that it holds within itself the entire condensed essence of the modern world, that will allow you to unpack it and rediscover and reinvent and rebuild and remake everything you need from absolute scratch. The book, in order to succeed within that premise, has to be entirely self-contained. You can't assume any external knowledge if you're restarting everything from scratch. But of course, that's an impossibility. You could never write one single book that contains everything you need to know, and allow you to rebuild this network of scientific understanding and technological inventions and innovations. And so writing the book became an exercise of finding that balance point between what is genuinely important, what actually is the foundational substance behind civilization, how it's progressed through history, to explain a bit of the science and history behind it, and try to balance that off against what is actually interesting to write about, or more importantly for your audience to read about. And there is, you may well have noticed, one huge area of human knowledge that has been building up over thousands and thousands of years that I basically ignore completely in the book, which is the whole body of understanding of mathematics. And mathematics isn't only this abstract, pointless exercise. You can use mathematics to prove these grandiose, philosophically rich theorems. But historically, we've also used mathematics for really down-to-earth, pragmatic stuff like designing bridges and buildings that don't collapse. And fundamentally, the reason that things like geometry were invented by the ancient Egyptians was how you can reliably carve out equal areas of farmland, fields, after the Nile has flooded and those floodwaters have receded again. So mathematics, of course, has been utterly critical to how we've built the modern world and how we progressed as a society and a species over thousands of years. The problem is it's now impossible to actually write about in a popular science book. And if you think about it, most of the most successful popular mathematics books of the last 10, 20 years have either been maths puzzle books that kind of engage you in that kind of problem solving way, or they've been books about mathematicians or about what maths has been used for, but they're not actually textbooks that tell you how to do those theorems and those mathematical processes yourself. So I had to make a decision quite early on to be brave about leaving out things which, of course, are important for the historical progression and development of the modern world, but just wouldn't hang together in a popular science book on the shelf of a bookshop you want someone to browse and pick up and ultimately enjoy reading.
Yeah, you don't want it to become a GCSE maths lesson with Pythagoras and SOHCAHTOA and so on. I come from a physics background, and I know that there's certain physicists I know who would answer this question by saying, well, you just write down the Standard Model and the Lagrangian, Newton's laws, Maxwell's equations, and all of civilization can be derived from that. But this is obviously a much more practical guide, or bills itself as a more practical guide to some of the things that you need to know. And in that sense, in some ways, it does resemble a history, because you have to go back and figure out what people were able to do and how they solved particular problems prior to having this whole apparatus of industrial civilization built around us, where the solution to most problems you encounter is to Google it and then order whatever the thing you need is off Amazon. So, I mean, what do you think was, in that vein, the most surprising thing you discovered in researching the book, the knowledge that you didn't have much appreciation of before you started, but which wound up being really crucial?
Yeah, so I think you're absolutely right about that point, that you might consider the best approach to this thought experiment is to write down all the mathematical and physical proofs that you think are important, and just allow some society that comes after this cataclysm to derive everything from first principles, which would be a noble academic exercise. But the point I try to make in the very beginning, the very introduction of the book, is pure knowledge is kind of useless to you unless you know how to apply it, unless you know how to make use of it, to be practical about it. And there's a wonderful quote by Richard Feynman, which I put in the beginning of the book, where he's got a single sentence answer to this question on the lines of, what is the most condensed kernel of knowledge that you could try to protect and preserve, such that some community of survivors after a global cataclysm are trying to unpack and recover and rebuild afterwards? And Feynman's answer to that was the atomic hypothesis, the idea that everything in the world around you, everything you see with your eyes and interact with and use on a day-to-day basis, is made up of atoms, of invisibly tiny particles that fly around very quickly and bounce off each other and repel each other normally, but can be forced to attract each other. And this embodies, in a very fundamental sense, a huge amount of physics and chemistry. But if I told you that when you're scrabbling around cold and hungry in the mud, what would you actually be able to do with that knowledge? You would die, philosophically enriched with that beautiful condensation of the physical theory of the atomic hypothesis, but it would still lead you to dying hungry and cold. So throughout the book, throughout the knowledge, I've tried to again strike another balance between deep fundamental truths, profundities that we've discovered in the history of science, and things which are actually useful. How you build a tool using this, how you can keep yourself healthy and provide for your everyday needs and requirements by applying that knowledge. And one of my favorite examples from the book, from the knowledge, of a tool which has been fundamentally useful throughout history and sits right in this center, right in the hub of the modern industrialized world today, is a very, very simple machine tool called the lathe, which you've mentioned already. And if you don't know what a lathe is already, it's basically a kind of a flat table, a bench, and on one side, let's say the left, you've got a kind of a disc with some kind of jaws in it that can grip the workpiece, whatever it is you're trying to work on, and it spins that workpiece round and round along its long axis. So if you're trying to carve, let's say, a table leg or a candlestick, or perhaps a cannon or the cylinder of a steam engine, you're basically performing the same function. You're trying to turn something and bring to bear a tool or workpiece back and forth along it. And that's basically what a lathe does for you. But what is amazing about a lathe is that not only can you use a lathe to make the components of every other machine tool that you'll find in any woodworking or metalworking shop today, and the very tools that allowed the Industrial Revolution, a lathe can make all of that, but it can also make itself. In a sense, a lathe is a machine that is able to self-reproduce in the way an organism is. It can make copies of itself. And even more amazing than that, you don't even need a finished lathe to make other lathes. A lathe can kind of pull itself up by its own bootstraps and make the components needed for its own successful completion, to complete its own construction. And there's a phenomenal demonstration of exactly that process of starting from absolute scratch, pulling yourself up by your own bootstraps, and kind of doing Minecraft for real, which was a machinist called Dave Gingery, who started with nothing more than a pile of sand, a pile of clay, a pile of charcoal, i.e. fuel, and a pile of old tin cans, of basically scrap aluminium. And by using those just raw materials, stuff you can kind of just dig up out of the ground, out of the natural environment around you, or smelt out of its ore, he constructed piece by piece a fully working lathe, and then used that first lathe to make every other piece of machine tool in his workshop, starting from nothing but some Minecraft piles of basic raw material, raw ingredients.
That's an incredible story, and I mean, there's another anecdote in your book about a guy who tried to build a toaster by himself as well for a project, and I think that was more to illustrate the difficulty that so many of us would have trying to do things without the support network of civilization, which has enabled us to be more productive individually, I suppose, by specializing in the ways that we do, but has also, I suppose, robbed us of this particular knowledge that you would need. I mean, there are communities, especially in the US, and we've mentioned them already, of these end of the world preppers who are convinced that society's days are numbered and are waiting for the breakdown of civilization and devote a lot of time to getting ready for it.
Yeah.
Did you engage with people from this community? Did you read their writings? And if so, how did you find that?
No, I absolutely did. I referred to a lot of kind of prepper websites, prepper books that have been written, and I have no personal issue with the prepper community as a whole. I just wonder, I just suspect if perhaps to a certain extent the prepper community is missing the point. And absolutely, I think they're right that if there were to be a collapse of civilization, a dissolving of the social order, of the social construct, there would be a period of unpleasantness. People would be running riot, it would be anarchy. Whoever had the biggest guns would be able to, lay claim to the resources they need, whether that was cans of food or anything else that they needed to make their lives comfortable. And I think undeniably that would happen. And that's what the preppers prepare themselves for. They stockpile not just bottled water and cans of food, but weaponry and shotguns and guns. And I wonder if there's a certain amount of just gun fetishism in the prepper movement. They're almost post hoc justifying their desire to have guns, and I'm happy for them. But I wonder if they're using this hypothetical potential of a collapsed civilization as a justification for needing those guns around the house. But I think what is often also overlooked is having lots of guns will be fine for the first 6 months, the first couple of years when you need to protect yourself and your family. But it's ultimately not going to help you recover your own society from scratch afterwards. You need to not only have a stockpile of, let's say, ammunition, but in the long term, you're going to need to know how to make the ammunition yourself when the rest of it runs out. You need to know what to do to make food come out of the ground in terms of primitive farming and agriculture when all of your cans of food have been eaten or you've drunken all the water. So to a certain extent, the knowledge picks up where I think a lot of preppers and survivalists leave off is day one, you now have nothing left. Your canned food has run out, your bottled water has run out, you no longer have any ammunition. What do you do now in this scenario to start making and crafting and building everything for yourself because your reservoir, your stockpile has now been exhausted?
That's an interesting point, and yeah, without talking too much about the prepper movement, it's interesting. I sort of have been when I was starting to look into the coronavirus crisis in January and February and so on. Everyone was discussing it in online forums. There were a lot of
Yeah.
preppers who flooded into those forums with all of their preconceived notions about what would happen to civilization, and none of which actually bore out. But it's interesting to see the mindset that some people have in this thing. So, I mean, I think as your book exposes and is sort of predicated on this idea that we live in this world where the division of labor is really hyper specialized and we all depend on each other and these networks that keep going utterly,
Yeah.
keeping the show on the road for so many of us to survive. Just as no one person could make a pencil, there are very few people, especially in the West, who would even survive for that long, you think, without this big life support apparatus from society, which comes across very strongly. So, I mean, and looking at a sort of historical approach to societal developments, we see that things like agriculture, mechanized agriculture, and all this sort of thing allow for an ever smaller number of people to actually do the work of keeping everyone else alive and keeping that life support system going, so to speak. Do you think that this is inevitable in the development of any society? And did you leave the process of writing the book wishing that we all had more of these practical skills? And what do you think people should know if they wanted to know something that would keep them going in a post-apocalyptic scenario? What skills do you think people have lost that they could really use?
Yes, so talking about the long-term history of civilization or civilizations, is that fundamentally, if you want your civilization to progress in a technological sense, so I'm not talking about the accumulation of kind of culture and art and philosophy and ideas, but a technological dimension to some sense of progress or becoming more complex or capable as a society. The first thing you need to be able to solve is how to grow food very productively so that all the members of your society aren't spending every day of their lives with backbreaking labor, growing enough food simply to survive in this sort of subsistence existence. You need to have, ideally, one person growing food for another 10 people or 20 other people in society, so that those other 9 or 19 people can go off. The majority of society can now specialize in doing other things, not growing food for everyone to eat, but specializing in craft skills like carpentry or metalworking or becoming a blacksmith or nursing and healthcare or chemistry and science and research and all these other niches and roles which we now have in our very complex, specialized, sort of niche defined society we have today, that all fundamentally descends from the fact that we don't all have to be in the fields simply to survive. And this goes into what sort of things that Adam Smith was writing about in terms of economics and how to make things more efficient in the mode of production, is that once people start becoming specialized in their particular role, the particular job that they do for everyone else, the particular favor that they provide to society, then as a whole, your society becomes more efficient, more productive. Everyone benefits in that sense. But a natural corollary of that is that every member of your society gets increasingly specialized and niche in their knowledge and doesn't really understand what everyone else does, which speaks to the point you were making just now about no one person in the world actually knows how to make a pencil, because all the different components of that pencil have been extracted from different parts of the natural world and processed and refined and machined in different ways to finally come together. And no one person knows each of those separate steps. So that, in a sense, is part of the problem. If civilization ever were to collapse, no one person knows enough of everything to start pulling itself back up by its bootstraps. And that, as I say, as a thought experiment, as a conceit, is what I'm trying to discuss and explore in the book.
So there are some interesting initiatives out there that do aim to record human knowledge in some of its aspects. You talk about the Svalbard Seed Vault, where we have some of the genetic information from these crops that we've crossbred over the years that are stored somewhere that's supposedly safe from the apocalypse. There's things like Project Gutenberg, Libraries of Congress, which digitize and preserve books and culture and so on. But your book does point out in ways in which these efforts have been sort of incomplete. And I think given now, post-COVID, it may be that people will be more willing to invest in insurance policies for worst case scenarios, just because they're realizing perhaps the really vital role that having a very small amount of preparation can actually do. If we had been more invested in pandemic preparedness, we could have saved ourselves a lot of costs now, for example. And it's kind of amazing, I've done series here in the past and talked to people who talk about existential risks and people concerned about how to program super intelligent AIs and all this sort of thing. But arguably, a lot of what they're doing is not actually doing things like this, where they're making preparations to kickstart this civilization reboot, so that if the worst things do come to pass, we wouldn't have to spend 2,000 years dying of communicable diseases again. So if you were in charge of apocalypse planning at the UN or some other major government, do you think there's any gaps that you would identify and organizations that you would want to see established, or things that you would want to be preserved in bunkers or whatever, so that humanity might be more ready for this kind of event?
Yeah, in a sense, there is absolutely nothing new about the knowledge about this science book, and even going back to the mid 1700s and the first encyclopedias that were being compiled as genuine attempts to document the sum total of human knowledge at the time. So, and Dennis Diderot, one of the first compilers of an encyclopedia, explicitly wrote in the introduction to his book that he was trying to preserve and protect and safeguard human knowledge in case there were to be some kind of catastrophe to befall the world, and say collapse of civilization, like the collapse and the fall of the Roman Empire. It was very much on the back of everyone's mind, the fact that civilizations are not infinite, they're not invulnerable, they do collapse, they do come to an end. And there's another zeitgeist during the Victorian era as well, that the British Empire would not go the way of the Roman Empire. And I think a lot of the kind of existential angst and catastrophic thoughts and apocalyptic thoughts all come back from that kind of Victorian anxiety about that. And if you were trying to write down all the knowledge you would need today, clearly I think that this is an impossibility. It might have been feasible in the 1750s, but we know so much more today. We've discovered so much more about the natural world. So perhaps you would do some sort of editing process of deciding what to leave out, and not try to capture, for example, the whole of Wikipedia, but choose which entries might be more worthwhile to preserve than others. And I think what a lot of written text overlook as well is this idea that knowledge in itself isn't necessarily all that useful to you. You need to know how to apply that knowledge, as you said already. And there's this whole idea of kind of knowledge and facts that you can remember versus sort of tacit understanding or practical understanding of how to actually make something. So, for example, you could give a 10-step set of instructions to someone about how to make a fishing net. But unless you can sit down next to an experienced fisherman and watch her make that net from scratch, would you have any hope of just following a set of instructions and doing it, just following the words? And I suspect the answer is probably not. So in the original encyclopedias of Dennis Diderot in the 1700s, they would show almost like cartoon panes, series of images showing every step in the process of making, for example, a fishing net. And in the modern world today, we can do far, far better than that. You could preserve a series of, sort of YouTube videos, little instructional videos that show all the steps of all the primitive stuff you would need to know how to do, and then building from that kind of foundational tier, how you can use combinations of those artifacts or objects or pieces of knowledge to make more complicated things, then more complicated things. And in a sense, you don't need some sort of top-down institution to be funded and start creating this reservoir of human knowledge and practical demonstrations, because people have been doing it off their own bat on YouTube already. And you can watch some absolutely phenomenally fascinating channels like Primitive Technology or How to Make Everything, which are demonstrating exactly these sort of things that we're talking about. It's happening organically. It's happening naturally.
It's interesting. I had to build this desk that I'm talking to you from now, from a flat pack from IKEA, and I'm just imagining the future, the post-apocalyptic future, as being watching YouTube videos, trying to figure out which tab goes into which slot for all eternity.
Yes.
Moving away from the knowledge then and towards astrobiology, which is your sort of main day job, I guess. The main way that we've covered this on the show is talking about the Drake equation, the various different parameters that go into it. So this is the equation that says, okay, the number of civilizations is the number of habitable planets times the star formation rate times the length of time for which communications, civilizations, and so on and so on. So what I want to ask you about that specifically is, do you think it's a useful way of thinking about astrobiology? And if so, or if not, do you think we're narrowing down some of those parameters there? What sort of questions are left open that keep you up at night, that keep you thinking about this? Because there's some of these parameters are in the realm of astrophysics and astrology, where we can say, okay, the number of habitable exoplanets, that's a question that we can actually answer with decent enough telescopes and decent enough astronomy. And some are really almost in the realm of philosophy, which are more whether and for how long civilizations would communicate or be visible to us. And some are in a sort of intermediate realm of biology, such as when life develops and when it becomes intelligent, which we might hope to narrow down, but we only have the one example that we know of to try and to work these things out from. So, I mean, how do you view that framing of the astrobiology problem, the problem of alien life?
Well, as a practicing astrobiologist, I would say that the Drake equation is abjectly and utterly useless. It doesn't really give you any meaningful answer whatsoever. But in fairness, Frank Drake never ever intended it to do so. And in a sense, I think the Drake equation has been misunderstood, misconceived by a lot of the kind of popular reproductions of it in TV series and documentaries. And everyone loves kind of plugging in a bunch of numbers and multiplying them all together and giving it a good mix in the cauldron and coming out with 1,000 civilizations in the galaxy. But there's the old phrase in engineering: if you shit in, shit out. If you don't have a good handle on any of those numbers in the first place, the answer that comes out is essentially arbitrary and meaningless anyway.
So it's not really an equation; it's a way of outlining the sort of dimensions of the problem, right?
Exactly. The purpose of the Drake equation was to break down this huge, chewy problem into a series of smaller problems which could conceivably be addressed and we could get some kind of good understanding of. And you did a very good job of kind of summarizing what the Drake equation is. And effectively over time, since the 50s and 60s, we've been filling in those numbers, working from the left hand, from the astrophysical parameters into the more of the planetary science parameters. And we are now getting a very good handle on star formation rate in the galaxy, the number of stars end up having planetary systems, the number of planetary systems that might have small, rocky, terrestrial, Earth-like planets orbiting them. The problem with trying to continue with that process, though, is that some of those terms are unknowable. for example, a probability that life arises on an Earth-like planet. You can't calculate that a priori. The only way that you could get a handle on that probability is by calculating it empirically, by, let's say, looking at 100 Earth-like planets in our galactic neck of the woods, counting the number of them that have life on them, and then getting a percentage out of it that way. So if you're trying to use the Drake equation to calculate the percentage or the probability of life in our galaxy, you already have to know the probability of life in our galaxy before you can get a number out of it. So in that sense, it is useless. But in the sense of breaking down a complex problem into smaller, more approachable tasks, it is a wonderful way of focusing your mind. And of course, the Drake equation as well is focused towards intelligent life and SETI, the search for extraterrestrial intelligence, whereas what I do in astrobiology and other astrobiologists are focused on is finding life in general. And we mostly care about simple, primitive, microscopic, single-celled life. Because A, that's the form of life that appeared on Earth first, and indeed was the only form of life on Earth for 2-3 billion years of the planet's existence. But also those forms of life, these microbial life forms, are so much hardier than big, vulnerable, multicellular life forms like you or I, or trees or forests or other animals. And a lot of what I do in astrobiology is studying extremophiles, these ultra-hardy microbial forms of life on Earth, and what they teach us about the possibility of life on other planets. What does it mean to talk about a habitable environment, an environment that life could get a foothold in?
So could you tell us a little bit more about extremophiles? I know that people will maybe be familiar with things like the tardigrade, the water bears, which we're told can withstand these quite incredible conditions. And then we also know of these bacteria that live in deep sea vents and don't really have access to sunlight, but they sort of survive off the carbon dioxide from these deep sea vents and so on. So when you're looking at these creatures, firstly, which organisms do you like and which are your favourite, and what sort of relates them to the habitats that exist in space?
Sure. So I mean, the tardigrades are often the poster child of kind of ultra hardy life forms and the possibility of life elsewhere. And I hate to throw a bucket of cold water on this one as well, but although undeniably cool, tardigrades again are kind of irrelevant when you're looking to the possibility of life on Mars, for example, or most other planets or moons we think might harbour life, because again, tardigrades are complex, multicellular animal life forms. And from what we understand about the evolution of life on Earth and the planetary conditions that are required, you probably have to wait around 3.5 billion years after the emergence of bacteria before something like a tardigrade can come about. And although tardigrades can survive very high doses of radiation and being blasted by UV in the vacuum of space and being dried out, that's effectively only because they're very, very good at going into a sort of state of suspended animation. They can form this dormant state called the tun state, which is very, very resistant to lots of different environmental hazards, but it's not alive in that state in any meaningful sense. It's completely dried out. It's not like it's crawling around in its little kind of microscopic water bear type shape while surviving all those environmental extremes. It's actually pretty feeble. It's just like us when it's alive and metabolically active. So this is why I say most of the extremophiles that astrobiologists get excited about, the sort of life that is actually alive and metabolically active under very hostile conditions, are microbial. They're ultra-hardy bacteria and archaea. And so that's the sort of thing we hope we might be able to detect signs of on Mars or Europa, possibly Titan or Enceladus in our solar system, and then maybe orbiting some of these other stars in the galaxy on extrasolar planets or exoplanets.
So what do we know of the history of the extremophiles that exist here on Earth? Because one question I've always wondered is it the case that we initially had life that began in some quite hospitable circumstance, and then extremophiles evolved from that to gradually adapt to a sort of an ecological niche where we have these quite extreme conditions? Or if the Earth turned into Venus overnight, we'd still have extremophiles that might survive here. But could they form? What do we know of the ones that live on Earth and how they came about?
Yeah, that is a really, really good point, Thomas, because Because when you think about it, all extremophiles really tell you is that life, once it's got started, once you've got cellular, self-contained, self-regulating life forms, once you've got cells, that life is very good at adapting to plenty of other environments, to very hot environments, very cold environments, very acidic, alkali, very salty environments. But that's only once that cell is formed in the first place. So perhaps extremophiles themselves are utterly irrelevant to the search for life beyond Earth, to astrobiology, because we kind of already knew that life is incredibly adaptable and diverse. And so perhaps the more important question is not what broad range of conditions different extremophiles can survive under, but what is the probably very narrow set of conditions under which a cell can form in the first place. And have those set of conditions existed on any other worlds beyond the Earth? And our current best guess, and there's a lot of controversy over the origins of life on Earth, but the
Hmm.
hypothesis that, as far as I'm concerned, seems to make most internally consistent sense, it seems to provide the richest answer to the question of how life got started, is that it got started around alkaline hydrothermal vents on the seafloor. So not the kind of thundering black smokers, which again turn up, you know, in every TV series about the astrobiology and the origin of life, but much more tranquil, cooler alkaline fluids, so-called white smokers, in places like Lost City. Because when you look at the chemistry that's going on in those hydrothermal waters in contrast to the seawater around it, we see a lot of very deep, profound matches between what happens on a fundamental level inside every cell of every life form on Earth. So perhaps the most important question is, did Mars, or the oceans on Mars, 3.8 billion years ago, did they ever have uh, hydrothermal vents like what we find in Lost City in the Mid-Atlantic ridge today?
Hmm. It's an interesting question. I mean, one thing that I think you quite often hear on this subject is that, and to an extent, I feel maybe I can understand why this is. But some people will say, we're making too many assumptions that life on other planets would have to resemble life on Earth and lead to similar signatures, and we should try and think about different forms of complex life that could exist, which might lead to different signatures. I mean, I know that obviously it's much easier to look for something that you know what it is rather than some completely unforeseeable form of life. But is this something that people consider in astrobiology? Or do you think that actually it's a sort of unfair assumption that there's just some complete category error and what we're actually looking for is completely different to what we're expecting to find?
I mean, it absolutely could be, but you're right that it makes sense to look for the sort of life that A, we already know is possible, i.e., life like us, that is a certainty. But B, we are very good at finding that kind of life already, because that's what we've designed hospital tests to do, to find life in place where it shouldn't be, like in your bloodstream or contaminating surgical equipment, or looking for hardy life in some of the most extreme environments on Earth, like the Atacama Desert, for example, where I've been on field work myself. But you're right. You perhaps don't want to be too blinkered to only look for life that is like us. That is one instance of biology, but it doesn't stand to reason that's the only possible instance of biology. There might be other biological systems, other ways of putting together the elements of the periodic table into self-sustaining, self-regulating chemical reactions, i.e. life, i.e. biochemistry. And if you look at alternatives to how we do it, how all life on Earth does it, you can think about whether there might be alternatives to DNA as an information storage compound. You might look as to whether there's possible alternatives to proteins, these long chains of amino acids which perform all the jobs inside the cell. They're the enzymes, the workhorses of the cell. But if you look on a fundamental level, we can be pretty confident that life on Mars or Europa or anywhere else we're likely to be able to check for the foreseeable future will be organic life. It will be based on carbon containing chemistry, um, simply for the reason that carbon is just so good at sticking to itself and other elements in the periodic table. It forms nice, stable bonds. It forms these enormous architectures of complex molecules like DNA that you need for life. And the closest element to carbon in the periodic table is silicon, is utterly rubbish in comparison. If you were to sit down with pad and paper as a deity to design life from scratch, you would almost certainly, reach for the carbon pot in your kind of palette of elements to design it with. As to whether life is likely to be water-based or not is a much more open question. Perhaps there could be other liquids that would serve as biosolvents, and ammonia is often talked about. But for the time being, we know that carbon-based, water-based life is possible. Hi, here we are. And we've got a very good knowledge of knowing how to find it. We've got the tests to look for that kind of life already. But whereas if we're talking about the possibility of life on Titan, which is absolutely sodding wet, it's drenched in monsoons and gullies and streams and rivers and seas and oceans, but none of that wet stuff is liquid water. It's liquid hydrocarbons, it's liquid methane and ethane. So one burning question within astrobiology at the moment is, could you have methane-based life rather than water-based life? Could methane support life as the wet stuff and serve the function that water does on Earth?
When we talk about trying to detect signals from life in outer space, what kind of thing are astrobiologists typically looking for?
When we're searching for signs of life on an exoplanet that we've discovered, and perhaps we've been able to characterize this world as being likely to be small and rocky, with water on its surface and orbiting an appropriate distance from its sun, so it's not too hot and not too cold, but it's in this habitable zone, the Goldilocks zone. So we found the sort of ideal candidate of a potentially life-harboring planet. The next step, using our telescopes, would be to perform spectroscopy on the light coming from that exo-Earth. We'd look for the signature, the fingerprint of different gases in that planet's atmosphere. We'd literally read what its air is made up out of. And if we see a mixture of gases like oxygen with perhaps methane, the best way we know how to explain that is as a biosignature. It is an indication that that planet is not only inhabitable, but is in fact inhabited. There is life, there's biology and biological processes going on that planet to release very reactive gases like oxygen are built up in the atmosphere. Now, there's a very separate question, which is what SETI is involved in, is not how can we remotely detect signs of biology and photosynthesis on other planets, but how can we detect technological life, civilization, intelligent, perhaps spacefaring life. That is not an area of research I've got any expertise in myself, but the sort of things that SETI astronomers talk about would be trying to detect unambiguously artificial signals, perhaps a sequence of primes being beamed and radio pulses towards the Earth, perhaps ultra-intense bursts of laser light being directed towards the Earth, something to be conspicuous and to catch our attention, but to then also be embedded, to be encoded with information that we could de-encrypt and perhaps sort of download a zip file of Encyclopedia Galactica and somehow work out how to decode all that information that some alien civilization might have sent us. And this is very much the script, the storyline of Cosmos, of Carl Sagan's book on exactly this scenario.
Or if not Encyclopedia Galactica, maybe the slightly less low market version, The Hitchhiker's Guide to the Galaxy instead.
Yes, slightly more sarcastic version of Encyclopedia.
Slightly more sarcastic, slightly more imbibed with alcohol version of the galactic knowledge. So no discussion of astrobiology is really complete without me asking you, and I know as a scientist you'd probably want to answer this question with a degree of uncertainty, so I'm going to ask for your opinion, which is the Fermi paradox as it's expressed is this idea about, okay, we don't know any barrier to technological civilization showing up aside from maybe a probability barrier. We're finding now so many exoplanets around so many different stars that it seems that planets are very common in the universe.
Yeah.
And so there's this increasing question of, well, where are the communicating civilizations? Where is the evidence for their existence? And Fermi himself was apparently concerned with the dawning of the atomic age and the zeitgeist of his time that maybe intelligent civilizations all find uranium and then blow themselves up before they can actually start communicating and becoming spacefaring. How do you resolve this fact that we haven't found any alien civilizations so far? Is it that we haven't been looking for long enough or far enough to find them? What do you think is the most likely resolution, in your opinion?
So my thought is that the reason we have not yet detected unambiguous signs of intelligent life in our galaxy is simply that intelligent life is not there in our galaxy right now. And I'm being careful about couching that answer to restrict it to only the Milky Way, only to our galaxy, and only at the moment. It might have existed previously in galactic history and wiped itself out, or just declined and passed away. In a previous epoch of the galaxy could have happened in galactic history, because there's a continuation of the Copernican principle that there is nothing special about Earth's place around the sun or Earth's place in the galaxy, but there's also nothing special about now. There would have been potentially life-bearing, damp Earth-like planets studded across the Milky Way galaxy tens of millions of years, hundreds of millions of years, a billion years in the past. And so life could have got started a long, long time ago. If there were intelligent life to have emerged in recent galactic history, it would have had ample time to spread from its cradle, from its home planet, colonized the entire galaxy in this, industrious, galaxy-spanning civilization. And so I don't see that intelligent life could be out there and be subtle and be hard to find. It ought to be out there, absolutely ubiquitous. I don't see any showstoppers in the laws of physics that prevent life spreading, albeit slowly, from one planetary system to a next, and eventually colonize the entire galaxy and being here, there, and everywhere.
So you view the absence of a sort of galactic civilization as evidence that, in fact, if there was a civilization in our galaxy, then it's declined, or for whatever reason never became spacefaring, or perhaps we're just the first ones to arrive in the galaxy, and there could be more in the future. I think so. I mean, in that vein, then, what would you say to other galaxies? Do you think there's probably life out there in some of them, given how many billions of them that there are? And would we have any hope of detecting things across that vast distance?
I mean, space is big. It is really big. And I could continue with the Douglas Adams quote if I could bring it to mind about, you might think it's a long way to the notable corner shop, but the universe is a vast place. That the galaxy, the Milky Way itself, is vast on an almost incomprehensible level for human scales and human conception. And the universe itself is absolutely enormous. So it would seem to stand to reason that if life could get started on the Earth, it could have started plenty of other planets and other star systems on the Milky Way or in other galaxies across the observable universe. But again, you have to be quite careful with that sort of slapdash approach to probabilities and how they work. Because if we go back to the Drake equation, again, as a way of framing how you think about it, if you deal with the entire observable universe, the numbers on the left-hand side of that equation become absolutely astronomical. They become enormous numbers, the number of potential stars and potential planets. But all it needs is for one of the other numbers in the equation, in that multiplication, to be arbitrarily small, then big number wipes out small number, and you're still left with basically one example of life in the observable universe, which is us. And until we can get a handle on the probability that life itself emerges under appropriate conditions, we have no way of guessing within many, many orders of magnitude how likely life is to be out there, how many other inhabited planets there might be.
And people have tried to do that. There was the one experiment with the I forget now, the lightning and the bottle of chemicals, and the sort of attempt to see if anything would spontaneously generate. The Urey Miller experiments, right? And you've talked about these vents where we believe life may have begun on Earth. So we do sort of have some conception of the chemistry. I suppose we could at least set in a sort of physicist terms a lower a lower bound, or what do I mean? I think I mean an upper bound on the probability that life would emerge just by observing a big vat of that stuff for long enough.
I mean, you could, and I've been involved in such experiments myself. Nick Lane at University College London is doing some fascinating research in the origins of life. And during one of my fellowships, before I got my own permanent post, I worked with Nick Lane, effectively helping him build a hydrothermal vent on the lab bench so we could do that experiment exactly as you described it. And Nick and his team have been able to demonstrate the production of formaldehyde, which is one of those fundamental organic compounds which is thought to be critical for building up a more important and interesting things like sugars and kind of nuclear bases for DNA. It's one of the stepping stones on the chemical origin of life. And let's say that his experiment and many other experiments like his around the world are successful in the year 2050, that we effectively brew life from scratch in a test tube by putting in a mixture of some simple organic compounds, giving it an energy source, stirring it up a bit, recreating a hydrothermal event, and 6 months later you hear a little kind of tap, tap, tap from inside of the test tube where there's a little bacterium, a little microbe has emerged out of nothing and is kind of swimming around now. That would be wonderful. That would be one of the most important scientific demonstrations in the history of humanity. We'd have created life from scratch. But again, when you think about it, all that tells you is one way that life can be created from scratch. It doesn't necessarily tell you that was our way of being created. We could have followed a different chemical trajectory. There might be an entire forest of chemical processes, chemical systems that can build up enough complexity to enable cells and life. And so what might be a very exciting development in the origins of life is being successful in many different ways in creating fully functional cells, basically out of kind of simple components, without trying to downplay just how mind-blowingly complicated that would be in the first place.
Mm-hmm. I mean, that's fascinating to hear that those experiments are going on, and philosophically, it would be interesting if we did suddenly manage to generate life over the course of 6 months, because although, as I'm sure you would say, it's very, very unlikely that would happen, it would then make you wonder if this process is actually that, relatively speaking, common. How many times could it have been replicated around the universe, and what would that mean?
Well, again, there's an
interesting questions to narrow this down.
There's an interesting corollary with the probability again there, that if you ask any organic chemist, if a reaction is likely to happen at all, it will happen quickly. And of course, there are some exceptions to that, but on the whole, if a reaction is kind of thermodynamically and entropically favored, it will happen quickly. So it's not like these kind of metaphors, analogies of a tornado blowing through a warehouse and all these different bits of components suddenly assembling themselves into concord. It is a process that ratchets itself up with more and more complex systems building out of simpler self-sustaining systems, and that could feasibly happen very quickly. And perhaps on primordial Earth, it happened quickly, and it happened independently in several different locations. If the conditions were appropriate on primordial Earth for life to get started once, it stands to reason it would have happened lots of times.
Because as I understand it, no good scientist would ever extrapolate from one data point, but we do think that life may have formed on Earth quite early after Earth itself formed, which sort of tantalizingly suggests that it's not a process where you do have to wait for trillions of years for it to happen, or at least we didn't have to do that here, is all we can really say about that.
Yeah, it seems as if life emerged on Earth as soon as it was possible for life to emerge on Earth, i.e. as soon as the environment cooled down enough and there was stable liquid water and oceans on the surface, and primordial Earth wasn't being battered in the face with huge asteroid impacts during the late heavy bombardment and all this rubble left over from the building of the planets and the formation of the solar system, that life seems to have emerged very, very quickly within just a few 100 million years of the ending of that late heavy bombardment. We have the first good signs, evidence of life on Earth, which doesn't mean it didn't emerge even sooner. It just means that's where we can put a flag in the ground.
So when it comes to the philosophical implications of your research, I find it so fascinating. If someone told me for sure, okay, alien civilizations exist, there's one in Galaxy 37b, or okay, life has actually formed on other planets in our solar system. The implications for that, I think, philosophically are huge. But also, if someone were able to tell me, okay, we know that our civilization and our species is the only one that's become intelligent in the entire universe, that has its own mind-blowing philosophical implications if that were to be true. I mean, is this the sort of thing that you think about, or are you just sort of concerned with answering these physical and biological questions?
Yeah, I mean, I think any scientist is concerned more with the day-to-day business of getting into the lab, getting your experiments done, getting the papers published, getting the grants coming in, and you try to find time for philosophical musings when you can. But I think it's Isaac Asimov that has got the perfect quote for this, which is either the universe is absolutely teeming with life forms like us, or it is absolutely silent and we are the only intelligent life. And both of those eventualities are equally scary, are equally terrifying. And I think it is likely to be one or the other. I think it would be odd if there were only, let's say, a handful of civilizations in the galaxy.
Yes, and you can think about the implications of either of those situations until the cows come home. So the last thing I want to ask about then is your latest book is called Origin. It's on the influence of Earth's geology on human development, which I think is the sort of question that when we're looking at exoplanets and their geologies, we might be thinking about how these things might influence the development of life generally. So it might be the sort of question that's considered kind of tangentially in astrobiology as well. I'm afraid I haven't read it yet, but I'm looking forward to doing so soon. Would you like to talk about it in a little bit more detail?
Yeah, so the book's called Origins, How the Earth Shaped Human History. And it effectively builds on from the knowledge. At the end of the day, the knowledge has got nothing to do with the end of the world or the apocalypse. That's just a way of framing the question and being able to explore behind the scenes of the scientific discoveries and the technological inventions that help build the modern world and provide for us in our modern existence. And what I've tried to do with the new book, with Origins, is pull out on that zoom, pull out on that perspective even further, and look at how features of the planet that we live on, planet Earth itself, have had a guiding influence, a defining role to play in the whole of the human story, from our very origins as a species and why we evolved to be so very exquisitely intelligent in the Rift Valley, in this tectonic fracture in East Africa, then across the millennia, the thousands of years of human history and the rising and falling of different cultures and civilizations and empires, through to the origins and emergence of modern nations, and how even features of the planet, of plate tectonics or atmospheric circulation or the distribution of resources, are behind headlines that you read about in the newspapers and current affairs that you hear about on the radio at the breakfast table. So Origins, again, I've tried to be very interdisciplinary, mixing between aspects of history and science, and within science, a bit of astrophysics, a lot of planetary science, geology, plate tectonics, biology, and evolution. So again, I've tried to write a mixed bag book, for purely selfish reasons that is what I was most interested to sit down and research and write about.
That's as I say, I'm really looking forward to reading it. I think if it's got anything on the knowledge, it's going to be a really wonderful read. I'd like to thank you, of course, for writing that book, and I'd like to thank you again for being so generous with your time today and answering all of the questions that I've peppered you with over the last hour. Thanks very much, Lewis, for coming on the show.
Thank you for having me. I've loved this chat. Cheers.
Thank you for listening to this episode. You can find Lewis's work at lewisdartnell.com, where you'll find links to his previous presenting work, his TED Talk, his academic publications, and various different multimedia appearances that he's made over the years. You can buy Origins and The Knowledge at all good bookstores, and I'm looking forward to getting my hands on a copy of the former, having devoured the latter one. You can also follow him on Twitter at Lewis Dartnell if that floats your boat. That's Lewis_Dartnell. Dartnell has 2 L's at the end. I'd like to thank him again for being so generous with his time for this interview. As for our show, you can find us on the web at physicspodcast.com. There you'll find all sorts of things. You'll find the new episode guide we have to all of the episodes that we've done in the past, the interviews, the series, and all that kind of thing. So it's a good thing for you to check in on if you're new to the show and you want to find out what our back catalogue is like. You'll find the contact form. Please get in touch with any comments, questions, concerns, people you'd like me to try and get to interview, topics you'd like to see us cover, things you like about the show, things you don't like about the show, all that sort of thing. It's a constant learning process doing this, and I want to keep improving as we move into the 3rd year that this show has been going. So thank you very, very much for everyone who does contact me via the contact form. I do try and respond to as many of those as I can get my hands on. Other ways to engage with us, of course, on the website, you can find there will be links to PayPal and Patreon if you want to support us financially. In the latter case, you'll get access to some bonus episodes. And of course, you can follow us on Twitter at PhysicsPod. The Facebook page is Physical Attraction, and the Facebook group Science Podcasts is still up and running if you want to find some more science podcasts. Of course, the most important thing you can do to support the show, rather than going on any of those social media channels, is to tell other people who may be interested to give it a listen. Word of the show is spreading, and I think it's spreading mostly by word of mouth, so I'd like to thank everyone who's done that already. Until next time then, please take care.